Is it on? Awesome. Thanks so much for coming. Hope you're having a great day, second day here. So I'm Thomas, coming from Harvard Medical School. I did my PhD in Geneva in genetics. I've been with Harvard Medical for 2 years, doing mainly hospital data analysis with a focus on NLP. I presented something last year here, semantic search, and I was talking about how hallucinations make it hard for researchers to work with LLMs, and now we're starting to have some projects where we're integrating it really in our pipelines, so hope you're going to be interested. I do use a bit of a lax definition of agents, first of all. We're not going to talk about LLM planning, orchestration, MCP. For here, what we mean of agents is integrating it in pipelines. So we'll have pre-processing and post-processing. What we really want to do is automate some high research impact tasks. We want reproducible frameworks that the clinician can understand and go into the details for when we want to make sure that the model is doing it in the right way. So I'll be presenting 2 main projects we've been doing, and there's some key steps, some similarities, and I think this is the really interesting part is out of all these LLM projects, what are the things that we always need to do, and how can we build some software that makes our life easier for every task but remains general enough. So I'll start with introducing a bit the problematic. So in research studies in hospital, we mainly have 2 kinds of data. We have the very codified structured data and the notes, comments from clinicians. So in the very well structured, you will have diagnoses, medications prescribed, the labs and procedure performed, the results from them. And in the notes, you'll have reports, justifications of why a medication was prescribed, why a diagnosis was performed. You will often have in these notes, oh, I'm suspecting this disease. The patient needs to follow up with this specialist. And so it doesn't mean that the patient has the diagnosis, of course. It's just a lead to build on to. And we see this problematic also in the codified data. So if you get a lab for testing your blood sugar, maybe the clinician suspects that you have diabetes, and you might have that in the codified data. So this is one of the pitfalls of the codified data that we address by having a look into the notes. If you have a look at papers of hospital research studies, you will often see how they define their cohort will be, I want patients with at least 2 diagnoses of this code, or 1 diagnosis and the usual medications prescribed. So there's usually a way to make sure that your patient cohort is, really has the disease. So yeah, this is what I'm telling here. And one of the things in our lab we develop is phenotyping algorithms. So here I'm explaining to be able to do a bit more accurate patient cohorts, instead of just doing, okay, 1 diagnosis code plus 1 prescription, we can have a look at the usual labs, the usual medical concepts mentioned in the notes, and we do a covariance based on this, and So we're able to do it a bit more in a more sophisticated way than just 2 diagnoses or 1 prescription. And to be able to measure these covariance-based methods, we do chart review. So we'll actually go into the patient notes, say as a gold label, did this patient really have the diagnosis or not? This enables us to say our algorithm has 90–95% accuracy, and then once we did this, we manually checked it on 100 patients. We scale it up to 10,000. So this is one of the usual case of chart review that we perform. And so more on agents, how we're using agents on the notes. 2 projects that my lab has worked on, medication history. So similarly as diagnosis, sometimes we have it in the code, but it didn't actually happen. In medications, it's similar. You might have insurance denial. Maybe you didn't receive the medication. These will be information that you will have in the notes. Usually the clinician will say, well, he didn't really start that. And so we're using LLMs to enhance the codified data on medications. And we also did one for heart failure phenotyping because it's an important contraindication in rheumatoid arthritis medications. So it's a key question for us. So now I'm going to start introducing the projects we're going to talk about in this hour. The first one is on inflammatory bowel disease, so Crohn's disease, ulcerative colitis. So the usual process will be that the patient will have a colonoscopy, and in the report, if it's all okay, you might have the clinician who says bowel preparation was fine, the colon is all good, and if you have moderate disease, you might have there was some ulcers in these regions, this region was inflamed, there was some polyps that were biopsied and were awaiting results. This is the typical report of a colonoscopy. And these can be useful to measure treatment efficacy. So let's say a patient has a moderate disease, starts taking treatment, then 1 year later he comes back, does the colonoscopy. Does he have mild or severe disease? And if he has mild, is that treatment worked? And severe, it did not. So this is the usual way to measure treatment efficacy that you will see in papers. And it is done manually by the clinicians. They will go over the report. They might have 300 sample size, so 300 patients, more or less. This is the usual treatment efficacy studies you will see in literature. So we're trying here to use the previously collected labels as our ground truths, train our agent on it, and then be able to apply it on a much larger scale on the full hospital. So from around 500, 1,000 patients, we go to 15,000, 20,000 patients. The second project, so I'm working on suicide prevention. One key challenge in there is the codes are notoriously challenging. One example is that the patient will come into the emergency department, has some injuries. The nurse will put them down and say, oh, well, maybe he needs to go to psychiatry. But then it's actually the psychiatrist who will make the diagnosis, this was a suicide attempt. And this is one of the reasons why we often don't see in the EHR codified data those codes that we are very interested in. And it's already a low rate event, it's rare, but even more we have missing codes. So what's actually happening is that we're including much broader codes, like broad injury codes, to make sure we capture a bit more, even if it means much more false positives. So this is something that is always done in the current studies in suicide prevention. And so we're hoping that our agents can enable to diagnose these, to identify when it happened more accurately than the codified. Another interesting point is that here we're looking at an exact date also. We're not just diagnosing, we want to know the exact date of the event because we usually want to put it in a survival analysis. So, describe a bit the overall problematic. We can start getting into the more agent think part of it. So why I didn't go with the usual agent definition that you will hear around here is that it leaves too much liberty to the LLMs, and we want to make sure that it respects our medical guidelines. It doesn't plan too much on its own. Some example of the limitations I saw was, so in IBD and colonoscopy, one thing you can see is the patient comes in, he didn't prepare well, he didn't do like often the patient needs to not eat for like 1 or 2 days. If he didn't do that, the report of the colonoscopy might say it was not feasible, so we're reporting it to the next week. He comes back next week, then you have it. So here you have 2 notes. So how do you process that? Do you put them all together in one prompt? If you do that, and you just ask the LLM to identify the date by itself, I was quite surprised, but the LLM often gets it wrong. Like, I get some dates, no colonoscopy attached to it. So this is one example where I don't want to leave this to the LLM. I want to keep tracking it myself. Another example of issue I was facing in suicide prevention. So there's a lot of subtleties in, there might be patients thinking about it, planning it. You might have self-injuries that are like just superficial self-injuries. And so trying to explain this in a prompt to the LLM is, he will get it wrong most of the time. One example is if he has superficial cuts and is thinking about it, then he will say, oh, that was a suicide attempt, but actually no. So to define these, it's important to have the clinicians that support you to make sure you're interpreting the clinical definition correctly. But so even for you as a data analyst with expert support, it's hard to understand. So for the LLMs, it's going off track completely. So here I want to pause on traceable AI, because it's not only about explainability and not even about reproducibility. Often what the clinicians will ask us is, show me the exact note that is supporting what you're saying. So you're saying that this patient had a suicide attempt at this date. Show me exactly. I want to double check it. We can also think about cutoff values, overfitting problematics. So we want to have a traceable pipeline where we can come back and say, this is why we made the decision. I think that explainable often just says these features contribute, but not necessarily what are the interactions between them. So this is how I feel there's a difference between traceable and explainable and reproducible. So here I'm starting with the example that I was mentioning. If we put several reports in one prompt, the LLM will not get it right. But we have to admit that it's doing a very good job on identifying the natural language parts. So mild disease, we can scale it to 1. Small ulcers, it will understand it's mild. So we need to leverage what we can and track as most as we can with the classic methods. So this is why I'm integrating it into a larger pipeline with an extensive pre and an extensive post processing steps. So safety alignment is also a big question, especially in suicide prevention. Last year I was mentioning that I was getting often safety errors when I was asking him to map suicide relevant features. So this does make it even harder to use commercial models because commercial models might have additional guardrails than local models. This is arguable, but it is something you will need to keep in mind. There will be some things that the LLM refuses to do. I saw this morning the Hollywood special effects talk. They were saying that when you're manipulating a video, if the guy has a gun in it, the LLM will refuse to do it. So this is another example of a safety. So I saw that this was a good moment to introduce my team. So Tianchi is my professor. We have Katrin that is in the rheumatology at the hospital. Ashwin, who is in gastroenterology. William, psychiatrist and researcher. And Huayuan is a PhD student in LLM and gave me quite some good insights in reasoning models that I will mention a bit further on. So we described a bit what we wanted to do, the chart review, the usual problems with agents. So now we can start thinking about how are we going to actually implement this. So this figure will probably be in a similar form in a paper quite soon. So in this one, I did it for the gastroenterology project. We have the first step, basic, select the nodes, build the prompts for each date. So we're keeping track of the date. We want to make sure each prompt corresponds to one patient and date. We're calling OpenAI GPT-5, parallel requests. Then we parse the responses. So we ask to output a JSON format. We convert this to CSV. We might have some request errors. We recall this sequentially to make sure it's not about token quota issues. Then the normalizing response is a big part that I'll come back on. And then we have a final rule-based medical inference. So now I'm going to detail a bit each of these steps. And so first of all, a little reminder on just setting clearly the specs. Preferably, we call it on individual nodes because we're able to keep dates. However, you might have too many nodes, too many patients. In that case, you might want to do just extracts, but you still need to call it individually on each patient to make sure you can come back to something. Here I'm giving some numbers. So in the suicide prevention project, our ultimate long-term goal is detecting, based on the nodes, every event over the lifetime. And the number of patients we're trying to scale to is around 1 million. And in this project, I was doing 1 year for 3,000 patients. So starting smaller, 1 year is defined because it's the 1 year post admission to a psychiatric hospital. So for one patient, 20 notes on average, and each note might be 10,000 characters long on average. So we're asking the LLM to output the information as a JSON to be able to parse it. To perform this, there's actually quite little models that will enable you to do this correctly. I did a few tests. There was some prior publications on Mistral OpenOrca 7B. However, I really wasn't able to get satisfying results out of it. I think maybe because I'm asking quite a few, I'm asking maybe 20 fields. So in the previous papers, maybe it was much smaller. From what I saw, only GPT-OSS and Chiwen, the parent model of DeepSeek, were able to output JSON consistently. You might want to try Llama 70B, but so outputting JSON was our core requirement. A few other considerations: context window. So I was saying a node can be around 10,000 character long. You will need something that takes this easily. I think that DeepSeek, the not too big models, has quite a small context window compared to GPT-OSS. So that was my my reason to move to GPT-OSS. The larger DeepSeek model in Chiwen, like 600B, are able to have similar context window as GPT-OSS, but the like medium size around 100B will be quite limited. GPU requirements, of course, and the country of origin can be quite important as you're deploying it in compliance environments. It might also influence safety alignment. So this is just some things to keep in mind. I can't really say, I don't have big numbers on this, but it's just something to keep in mind. Yeah, GPT-OSS 20B fits on a 50 gigabyte GPU. You will need to think that your context window does take quite some impact on your RAM, so you can't just barely fit it. And 120B on 2 GPUs should be fine. And for commercial models, so Azure has HIPAA compliance, and so this will be something you will need for medical applications. So in these projects, the gastroenterology one, I'm doing it with OpenAI, and suicide prevention one, I'm doing it with GPT-OSS 120B. Then to actually run these models, you have 3 main choices: Ollama, vLLM, SGLang. I started out with Ollama, but to do inference on thousands of prompts, vLLM really outperforms it. I haven't tried out SGLang for the moment. I hear that it's better on multi-GPU settings. So a little background on reasoning models. So we had large language models, let's say Llama 7B, and 1 or 2 years ago, one of the big hot things was chain of thought, and this enabled the LLMs to get much more accurate. How it's performed is you basically have the same under first layer of transformers, but then you're fine-tuning your model to describe precisely the steps it takes to get to the answer. So this is chain of thought, and by extension, reasoning models. This is much better, but it is also computationally much more intensive. So depending on your task, you might also just stick with a non-reasoning model, as it will be much faster. It does changes a few other things. You don't have a temperature parameter anymore. In some models, you might have minimal to maximal reasoning. So 7B is not a reasoning model. Mistral Open Orca was some early prototypes of a reasoning model. And so in the commercial models landscape, GPT-4o, for example, is not a reasoning model. It will be much faster. GPT-5 Mini is, and you can have several levels of reasoning, 3. And I think that GPT-OSS, you should be able to specify the reasoning level, but I think I remember that vLLM was explicitly saying that it's not supported, so you just have default for the moment, medium. And so I was saying that you might want to do non-reasoning models for some tasks. And it does highlight that often when we talk about AI, we talk about reasoning, so calculations but for me, the LLMs are also very useful just as NLP tools. When I'm doing mild or moderate disease maps to 1, it's I would say it's a bit arguable. Of course, the border is hard to put, but the point I'm making is that you can do some AI projects with a little input, and that's what I call reasoning heavy. You don't have much things to explore, and you can do NLP projects with so a huge amount of input, and then you're rather in the NLP domain. You're rather trying to extract some concepts that you'll further pre-process, post-process. So I do kind of like to distinguish the reasoning heavy, the more usual AI, what we think about, and the still relevant NLP tasks of identifying concepts and doing more of the reasoning yourself in your pipelines and your algorithms. So that was for the concepts. Now we have a bit of all our tools. We're ready to get the hands dirty. So coming back, I was saying select nodes. So input selection. One of the key part here, retrieval augmented generation. So you have large inputs. They are chunked. You store them with embedding models. When the user inputs a query, you retrieve the most similar chunks. So if you have 1 year of nodes of patients, you can just select a few and just feed that to the LLM. If you feed everything, you won't be able to scale. I'm moving towards a second way, not just semantic similarity, but also merging lexical similarity. So hybrid search. This can be exact or approximate string matches. It's very, it's the kind of the old way of doing search, but it is useful to address the limitations of embeddings. One example of embedding limitation I'm seeing is for the LLM and the embedding models, suicide attempt is really a psychiatric disorder. So it will be very close to psychosis, hallucinations, and maybe if you have something in the note like cut himself, he will rather classify that as a small injury, and you might not have it very similar to suicide attempt. So that's one example of the limitations of embeddings. And another important thing is when the maybe it's rare term that doesn't have much semantic meaning. So this is where lexical and hybrid search helps you a lot. I performed this with OpenSearch, fork of Elasticsearch. There's a few other talks these days on OpenSearch. Some usual software to do these are Milvus and Chroma. There was a nice a talk talking about comparing the performances between all these different choices. For me, it's also that OpenSearch can do hybrid search out of the box, whereas with Milvus and Chroma, you would need a second system to combine them. So that's ease of use for me. This was my little test ground for hybrid search. I started out with 350,000 abstracts of papers. So in abstracts, you might have 20 sentences. I chunked them by 3 sentences. In final, I have something like 2 million chunks. I embed these with BGE. It's an embedding model with 1,000 dimension. And my little API is you put in a query. Here the query is BLK-gene. And here is the output. So you have the article to the PubMed application and the little chunk that had the highest similarity. And in this case, the 2 first hits were actually from the same article. So this was input selection. Now we're moving on to building prompts. So the basics, you describe your goal and task, your expected output, you give a few input and or output examples, especially outputs. And once you did a few runs, you might want to integrate additional considerations of errors that you noticed. There are some little tweaks around this. A famous one is, if you do it correctly, I will tip you $1,000. I saw another one earlier where it was saying your mother has cancer, you need money. Personally, I don't do this, but I do use repeating some instructions. It doesn't necessarily work. I have some examples of a friend that was even like writing it 20 times, do not take into account this, and still ignoring it. I try to just repeat a few times, you should not take this into account, this contributes 0. This is a nice moment to introduce DSPy. Maybe show of hands, anyone heard of DSPy? 1, 2. So DSPy tries to abstract out this prompt engineering. So let's give an example. You have some input emails you want to classify high, low priority. You have 100 emails. You give him 100 labels. This one is high, this one is low. And so DSPy will try to make up a prompt on itself to classify correctly. You don't even need to give him a seed. You don't even need to ask him to output something that is human readable, but you can, if you want, you can start with a seed and you can ask him a readable output. Yeah, I haven't tested it yet. I'm thinking that for medical considerations, it might overfit. So yeah, I don't want it to just focus well on my few 1,000 cases when I'm gonna scale it to 20,000 patients. I want to try to keep some human/medical reasoning behind. So once you have a prompt, you're ready to call your LLM. I'm using vLLM, I was mentioning. We start by initiating our endpoint. I'm using Podman. It's a rootless Docker. It's good for shared environments. In this little snippet, I'm using 4 GPUs, GPT-120B, deploying it on port 9010. The no enable prefix catching might save you some time. I won't elaborate too much on this, but we can come back to in the question. And yeah, 0.15 Docker image, and we cage the model to make sure we don't download it each time. So now our vLLM is running on 9010, and we can call it with any post query. I'm using R. This is the example of how I build my query. I have a function with my prompt coming in, and this I build my body, retrieve the result, and get it back from the function. So we waited a few days, a few hours. We got the LLM output back for all our inputs. We have our JSON objects, and now I think it's the interesting part of normalization. So one of the things I saw was I was asking him, if you have ulcers, you put one in with the field name of ulcers. And 20% of the time, it will work 80%, but 20% of the time it will tell you presence of ulcers equal 1. So when you're trying to put that as a final CSV, it will break your thing. And so you have maybe 5, 10 fields you want to identify. So you have some randomness that you need to take into account. You need to have an automated system that will map them correctly to the box you were expecting. You could just recall the LLM, but it would be quite a lot of calls. And most likely you will need, in any case, one mapping at the end. So I was doing it with string distance, regex, but one of the things is that at the beginning I was doing it like on 100 patients. I still had some labels I hadn't looked at. When I scale it to 1,000, oh, there's some new cases that I didn't manage. Is it still going to work when I'm going to do it on 20,000? So I think that here, this morning, the concept introduced was human on the loop. It's not necessarily in the loop in the sense of we're not waiting for a human to say yes or no, but we do need a human to go over some of the logs. So one of the questions is, how do you make logs that you will be able to review easily? So this is my traceable mapping table. In the columns, you have the 5 boxes I want to get to. And in the rows, you have what was actually returned by the LLM. So in here, it's like on 100 cases. It's not that much. In the next slide, we'll see a bit more. But we already have some examples in the second part, narrowings, example stenosis, narrowing stenosis, surface disease, surface involved by disease. So these two should map together. And so I'm doing little regex plus string distance matching. And I'm double checking that, okay, these three first, they correctly went into narrowings. These two, they correctly went into surface disease. These two went into surface ulcers. So that's how I'm doing the human on the loop, the traceable mapping. And so when we go to 20K, this is what it looks like. So you can't be able to think about every case that's going to happen. You need to just try it out. But I was lucky. From my 1,000 to 20,000, I didn't need to change anything. It's more when I was doing the 100 to 1,000 that I needed to review some of my code. So here in the first four, we can see there was 2,000 that was actually the correct field from the beginning, but almost 1,000 that were not. So if you're recalling that much, it makes a lot of further calls. So I think that you shouldn't just like recall 30% of your prompts. You should rather find good mappings. So now you have your nice CSV. That was I think the main conceptual part that I found interesting. Then we have a bit more medical intelligence. Maybe you were asking about ulcers. A second field is surface affected. The LLM told you, yes, there's ulcers, but it didn't tell you about the surface. So I'm adding some little rules. If you had one here, you will need at least one here. A last part, uncertainty and estimation. So it is inherent in the domain. The clinician might say, yeah, it's a bit in between. So you need to have a system that can manage this, and in your evaluation, it's good to take this into account to not underestimate too much your performance. How I started doing this was 3 independent prompts, low, average, high estimate. So let's say the node says mild or moderate. In the low one, you would take mild. In the high one, you would take moderate. In the average, you put 1.5. So in the first case, I was doing independent calls. The nice thing is that you can see some randomness in the LLM. Like you might ask him for the low and the high will actually be lower than the low. However, this does increase by 3 times the number of prompts you need to make. So in our scalable version, we're just doing it in one prompt, asking for 3 estimates. But on our, like, if we want to really focus on 100 patients, we can do three calls independent. Then once I have these estimates, if they all agree we're good, if they don't agree, I'm flagging it. It might go for manual review by the clinician. It's usually like 10%. So here we're a bit coming to the end. This should be clear by now if you have more questions about it. So build the prompts, call in parallel, pause the response, normalize, rule-based medical inference. The cool applications of this, treatment efficacy measurements on much larger populations. So we performed it for around $300 on 50,000 notes. This was with the OpenAI GPT-5. If you don't really have GPUs, I recommend it because it will be easier to get you started. However, if you want to move in a more intensive, it might be worthwhile to invest in the GPUs. Maybe a box you can count around $50,000 to get a box. So treatment efficacy in inflammatory bowel disease and for suicide prevention, increasing the reliability of the codified data. The core experiments I did previously, 2 or 3 days with 4 GPUs to do 1 year of notes for 3,000 patients. We were estimating to reproduce it on the Google Compute would be likely around $2,000. And we're now working on scaling this to get to something that we can run on 1 million patients on their lifetime. So here, what I was saying on 2 or 3 days, I was doing every note, full notes. And now we're trying to do just extracts, just the notes that are interesting, the psychiatry notes. And this is where hybrid search comes into play. So the GPUs were kindly offered by the Center for Suicide Research and Prevention, collaboration between Mass General Brigham and Harvard. You have Jordan Smaller over here in the middle, and my professor is over here in yellow. Some cool ideas I'm working on currently. So when I'm doing note selection for the case of 1 million patient over lifetime, currently I'm doing some heuristics to narrow down on the notes of interest. We have too much notes to process them all, even by just selecting extracts. I'm thinking that maybe agent could help me in there to focus on what is the time period that I should focus on.
Sorry, I didn't see that.
So currently I'm doing simple heuristics. Maybe the agents could help me increase performance. And the really cool, more long shot project I'm thinking about is, so for prediction of mental health disorders, DSM-5 has some questionnaires to evaluate personality traits. So personality traits can be measured in various ways. Facebook models you by your likes. The usual model you might hear about is Ocean. You have like openness, extroversion, neuroticism. Each of these are usually linked to one mental health disorder. So it's like, if you're very neurotic, you might be schizophrenia down the road. Autism has a bit of links with obsessive compulsive disorder. Bipolar has some links with impulsivity. So they are quite relevant in the medical domain as well. DSM has a list of 200 questions, and then they say, okay, if you answered in this question, this goes to this personality trait, you sum them up together. The guideline is that the clinician should ask the patient to do it every 6 months over 2 years, and if it's consistently high in one personality trait, then we might want to investigate. Maybe the patient doesn't have a formal disorder, but some problematic personality traits. So this is how DSM suggests to use it. And how I'm thinking of using it is trying to answer these questions based on the notes. So let's say one of the questions is, I'm a risk taker. This gets mapped to impulsivity. In the notes, you might have various things like the patient ran away from home, he's a kid, he's in conflict with his boyfriend, here the example I'm saying is jumped over a fire pit at a party. You could think is like not very relevant, but it can maybe help you answer the question of I am a risk taker. And so I'm thinking that this could be a cool way to model personality traits based on notes and try to predict better mental health disorders with that. Thanks a lot. Any questions?
Yes.
I have a couple questions, but I'll start with this one. You mentioned chunking based on an arbitrary sounding 3 sentences or 2 sentences. Does chunking have to be done blind like that or naively? Or can you use an LLM to sort of chunk for you based on thoughts, or concepts?
It makes me think of, I think, contextual retrieval, where you're using a chunk, but you're also asking the LLM to summarize a bit the chunk above and the chunk below. However, one thing maybe you need to keep in mind is that we're doing chunking for the retrieval augmented generation, because the retrieval augmented generation, like the RAG, the embedding part, is more computationally efficient than calling the LLM. So I think here we're trying to do this to not have to call the LLM on everything. So it's not really the goal to call the LLM to help us on the chunking, because it's computationally expensive.
Hi, my question is, with reference to neurology and depression, connecting to suicidal tendencies. I attended a session on deep brain stimulation, where they are able to detect depression and also to treat it. That means that they are able to read brain signals and infer that there is a cause for severe depression. My question is, can such information be combined with your AI efforts and conclude to a more concrete decisions and conclusions?
Yeah, I would say these sort of signals are very real time, and my signals are but more long term. So definitely can be used together. It does make me think of maybe when you are able to measure depression, let's say you're already a bit in the zone of not acting a lot, maybe staying in bed, and maybe the important part, at least for me, is how to intervene before you get into the zone. So I'm just maybe that's one limitation of the brain-computer interface.
You mentioned more legacy LLMs and then now reasoning LLMs. Are reasoning LLMs runnable locally? Or if you want to use a reasoning LLM, are you forced to use an API?
No, the OSS, GPT-OSS are both reasoning models.
And it works with Ollama or vLLM?
Yeah.
Questions, anybody? More questions? Yes, back there. Okay, there we go. For these notes or the charts, how
varied is the language? Like, do you really need large language models, or can you constrain what it needs to look through a small language model or something specific to just this area of exploration, and then not have to worry about others? The reason I'm thinking is maybe you have a small language model for the IBD and another one for something else. Would they encompass enough information to give you results?
So should we use rather two different small language or one large? From what I see, you do need a lot of general knowledge. So I'm a bit afraid that the smaller don't have that. In the IBD project, it's probably not a big deal. You might be able, because you mainly rely on a few synonyms like stenosis, that means narrowing. That's important that your language model knows about that. Other than a few synonyms like this, you don't need that much reasoning. In the suicide prevention, however, there's also like very various cases that you will come up into the notes. And I'm a bit afraid that if you fine tune too much on one case, you might lose the generalizability. I do agree that it could be cool to measure the difference, because you would probably get much more computationally efficient. So that's the really key thing that would make you want to go into that direction. So it could be cool to compare either a RAG with GPT-120B or a small language model, and you don't need a RAG. So I think that would be relevant to test.
Any more questions? Questions? Well, thank you. Excellent questions. Excellent presentation. Thank you very much.
Thanks all.
Yes.